Okay. Good morning and welcome to the second plenary session. The first talk in this session is by Neeraj Gupta, who will tell us about Meerkat absorption line survey.
No. Yeah, cool.
It's fine?
Yeah.
Right. It's on.
That was on.
Yeah, this is on. Yes, it is changing. And there is a pointer.
There is no pointer? अच्छा
This is a
separate
better
है.
one.
Okay. ठीक है. Okay, hi, good morning friends. I'll talk about Meerkat absorption line survey. This is a large survey project running on Meerkat telescope, which is currently the most sensitive telescope at centimeter wavelengths. And for given size of project, this is a pretty small team. It's all geographically distributed, bringing in lots of different types of expertise that is required to carry out this survey. So I'll start with a very quick intro to what is Meerkat and what is MALS. So Meerkat array, as I said, currently it's the most sensitive telescope at centimeter wavelengths. It's situated in South Africa. You can see some of the dishes of this telescope. It's a radio interferometer. And as of now, it consists of 64 dishes, which are in offset Gregorian configuration, which means that the feed is off axis. And you can see from this diagram here that of the 64, 70% of these are actually centrally concentrated. And rest of them actually extend out to 8 kilometers. So what this means is that it gives an excellent surface brightness sensitivity to the telescope, and at the same time it also has a very high spatial resolution. And the telescope itself is situated in a very remote location, which means that it gets very low radio frequency interference. It has currently got 3 receivers. L band goes from 900 to 1670 megahertz. UHF band goes from 580 to 1015 megahertz. And S band receiver, which is new, it just has been commissioned, it's getting released. And Meerkat itself is undergoing a further extension. Very soon it's going to have another 20 dishes, which will go out to 17 kilometer. And Meerkat is actually SK precursor, so in a few years' time, it will actually become part of SK phase 1 as well. And from the correlator perspective, it has got an instantaneous bandwidth of 32 of about, it can cover the entire band actually, L band or UHF band, whichever we want to observe, and then it can provide 32K frequency channels in that. So this means that we can cover very large bandwidth, and we can also at the same time have very good spectral resolution. From MALS survey perspective, we are interested in observing two lines. One is H1 21 centimeter and another is OH 18 centimeter line. So main lines are coming at 1420 megahertz in case of H1. In case of OH, we are talking about approximately 1667 megahertz. And if we convert this into redshift, this means that if we use these two receivers, we can cover redshift of 0 to 1.4 for H1, and we can cover redshift of 0 to 2 for OH lines. And this is very much the main objective of Meerkat absorption line survey, which is to carry out a blind search for these absorption lines, and using these put constraints on the evolution of cold atomic and molecular gas in the universe, of course over this redshift range. So it's a large project, as I said. It has got 1655 hours of observing time at both these bands, and in total we are going to observe approximately 400 pointings as part of this survey. Over 2017 to 2020, we carried out commissioning and science verification, and the survey started in 2020. As of now, we have observed all the 400 L-band pointings, and as you can see it from here that the configuration which we are using, 1 hour of observations corresponds to 1 terabytes of data. So this means that for total observations of 1655 hours, we are expecting a raw data of just 1.7 petabytes. And for the total survey, which means that if we also want to count in various images, data cubes and everything, the total requirement will go to 8 petabytes, which will also include all the elements that we want to include in public data releases. So it's a kind of a massive endeavor from the data management perspective also. So from the primary science objective perspective, we all know about this, that observationally it's very well constrained, that star formation rate density shows this rapid evolution, especially over the redshift range of 0 to 2, and that's what we are targeting here. AGN activity, if you also look at it, also shows a rapid evolution over the same redshift range, and we know that if galaxies has to sustain the observed star formation, they have to continuously accrete gas from IgM and CGM, and at the same time should also be able to convert this atomic gas into molecular gas from which eventually stars can form. And you can see from this panel here that H1 mass density itself actually is not really very rapidly evolving over. But if we look at molecular gas constraints which are coming over last few years from ALMA, NOEMA, and various other telescopes, it does show some a similar evolution that we see it here in that sense. But there are still several gaps in our understanding of how the H1 which is present here is getting converted into molecular gas and then into stars. And there is this intermediate phase which we can think of can be observed through H1 21 centimeter absorption and also the OH. And that's the reason that why we are targeting these two transitions. And another thing to consider is that cold gas will always be accompanied by dust. So this means that any observation that we want to do for this kind of science objective has to be dust unbiased, and that's the kind of effort people are also putting, even if they are carrying out these projects in optical and ultraviolet wavelength. But in radio, that's a natural advantage that comes in, because since we are observing at longer wavelengths, we don't have to really worry about dust extinction. So that's one of the major strengths of carrying out these studies at radio wavelength. So a couple of things I would like to say about how do we optimize a survey at for a spectral line survey. So this is consider this configuration, that there is a bright quasar at a certain redshift, and as the light from this passes through all this intervening medium and reaches an observer, it is going to also carry imprint of various absorption lines that can come from the gas that it encounters in between. And if the sight line passes closer to a dense clump or a galaxy, then it would produce this strong damped line of absorption, which corresponds to column densities more than approximately 10 to the power 20 per centimeter square. And that's the kind of column densities that we see in the H1 disks of galaxies. So that's the kind of picture we should have in mind. And then this gas is also enriched, so we will also see absorption lines that are coming from metals. And obviously, since this quasar also is embedded in its host galaxy and surrounding medium, we will also see absorption lines corresponding to that. So using this kind of a configuration, we can probe gas that is associated with AGN as well as any intervening medium, both of these. That's quite convincing. But then whenever we are carrying out an observation like this is just one sight line, right? If you want to make connection with galaxies, this means that we have to do it in a statistical sense, which means that we need to observe large number of such sight lines to be able to build a big picture. So for that, the quantity that we need to optimize is the co-moving path length, that the total redshift path that a survey would cover, which essentially is corresponding to this redshift Z1 and Z2. That's what we can think of in very simple terms. So redshift path is corresponding to that. But when I am using an instrument, my instrument will not have uniform sensitivity across the entire band. So this, there are two terms in this here. This term is just the underlying cosmology. And this G term actually is corresponding to the sensitivity that is varying across my spectrum, which means that in certain part of the spectrum, I am able to detect only lines which are stronger than certain optical depth, right? So if you want to maximize this quantity, this means that we need to select objects which are as far as possible so that I am covering more and more redshift path here, and at the same time I must select sources which are bright enough so that my data is also sensitive enough to detect the kind of gas that I am interested in, gas column density that I am interested in. So we have done this kind of optimization for MALS, and if we compare it to whatever that has been done in past, we anticipate a 10 to 100 times increase corresponding to the redshift path. So this is one of the prime reasons we believe that through MALS we can put very nice constraints on the evolution of cold gas in the universe. And of course, we have very seamless coverage up to redshift of 1.4, except for some small gaps which come at lower redshift due to RFI. And that's something I'll show later. So now we know how we want to carry out this survey, but still there is more work to be done to define in which directions we want to point our telescope to. So the survey is well underway. As I already showed to you that L-band observations have completed. So what I'm showing you in all these slides from here onward is actually the real data. So this is one MALS pointing. Right. So at 1.4 gigahertz, Meerkat's field of view is approximately 1 degree. That is just the FWHM. You can go far out with a lower sensitivity. And in this pointing itself, there are 4,000 sources. So if we take up all the data that will come from 400 pointings for L and UHF, we will actually be detecting more than a few million sources. And we are talking about sensitivity of about 15 microjansky per beam in continuum. And this sensitivity is particularly interesting because if I go to 15 microjansky, which means that I am sensitive to detect sources reliably up to above 50 microjansky or so, this means that half of the sources that I am seeing in this pointing are not just AGN, they are actually star-forming galaxies. And that's very nice because we would like to be able to probe both. So this is one demonstration of it. I said there are 4,000 sources here in this, but only about 100 or so of them or few hundred of them are actually brighter than 1 millijansky, and these will become the primary targets for absorption line search because they are strong enough so that I can actually get sufficient optical depth sensitivity. And the slide and this panel on right is actually showing what has been done till now. These points represent whatever observation that has been done till now. So we are looking at something like 500 measurements that has been done over last 30, 40 years. With Meerkat survey, we are anticipating that we will have approximately 200,000 AGN actually covering this entire parameter space which has not been explored, and then we can actually relate this to various AGN properties and understand how cold gas is actually playing a role in evolution of AGN. And this is part of Partha Dekka's PhD thesis, who gave a MALS talk earlier in this meeting. So now let's quickly look at how is it that we want to select the pointing. So if I go back to this, each MALS pointing at the center of it has an AGN brighter than 200 millijansky, and then everything else is serendipitously coming in the field of view. So idea here is that towards the brighter source, I am actually sensitive to gas which is very low column density, which is this 5 into 10 to 19 per centimeter square. And then there are all these fainter sources towards which I can detect gas at higher column density. So idea here is that using an ensemble of all the sources there in the field of view, we can actually probe the entire column density distribution. But there is still a challenge that because over the entire sky, there are about 15,000 sources which are brighter than 200 millijansky. Which ones to select? So what we have done is that to preserve the dust unbiased nature of our survey, we have selected these bright AGNs on the basis of mid-infrared colors, because just like radio, mid-infrared is also unaffected by dust extinction. And plus, we can actually identify a parameter space here where we can not only select powerful AGN which are not dust extincted, but also at the same time have a higher probability of being at redshift greater than 1 or 1.5, because that's something we also want, as I explained before, to maximize the redshift path. So we select thousands of AGN in these, and then we carried out our own survey with South African Large Telescope. This was a large program which we carried out over 2015 to 2020, and we also took some observations with Nordic Optical Telescope. We observed a sample of about 400 AGNs, and from that we identified these different quasars. This is just showing how we went through the selection, went about selecting these sources. This is the redshift distribution of these AGN, and this is how our pointings are decided. And if I just show you that how convincing it is in terms of the progress that we have made in selecting these targets. So these three panels are showing what people have actually been trying to observe previously. So this black curve shows that, and blue curve is actually corresponding to the underlying population of AGN that we expect. So you can see that we have done a pretty good job of actually matching our target selection with respect to the underlying properties of the underlying population of objects. So on the sky, this is how the survey footprint looks like. So we have selected a total of 650 pointings, and from which we are selecting 400, because idea is to have some flexibility, because as we know that when we are observing with telescopes, then it's nice to have some flexibility so that we can take advantages of gaps in different LST ranges and things like that. Right, so pluses represent these 650 pointings, and squares and the circles here actually represent the ones which have been already observed, those 400. And as of now at UHF also we have observed 200 pointings as well. So I would say that we are 70% complete in terms of observations. So just like we obtained spectroscopy for the central sources, and we all know from astrophysics that if you want to understand the physical conditions in interstellar medium or IGM, it's not just sufficient to have any one particular line, whichever band it may come from. It's necessary to have multi-phase probes, so which means that essentially we also need lots of other spectra for various other targets which are in the field of view. And it's not possible to carry out such large programs by just applying telescope time and getting one object at a time. So what we have done instead is that we have built partnership with ongoing large IFU surveys. Through DESI, we are observing as secondary targets about 50,000 AGN. We hope that's what we will be able to get over the period of next 4 to 5 years. DESI is already underway. And in foremost also we are deeply involved, and here we expect to get about more than 200,000 spectra from this survey. And with foremost we are, as you know that foremost is actually just getting on. Science verification commissioning will start 1 year from now, so here we are involved from very early stages, so we have much better handle on which targets to will eventually get observed and things like that. So this is what it is. This is actually the footprint looks like. 1655 hours, I said 1.7 petabyte of raw visibility is coming over period of 4 years. Total requirement 8 petabyte over 5 years. So what we need to do actually to make all the science happen from this data is to generate calibrated visibility, spectral line cubes, and if you want to do also polarization, which is very much in part of our scheme, is to do full Stokes continuum imaging, and of course include we also want to publicly release all the data products as well. So this brings to MAL's big data challenge, that is how do we tackle all this large amount of data. So 1 hour produces 1 terabyte, so just raw data itself corresponds to 1.7 terabyte, and we want to produce this Stokes I spectral line cubes, 3K by 3K pixels, so these are huge terabyte size cubes, and then IQUV wideband continuum images, that's what will give 1 million or few million continuum sources. So what we have done to handle this, because this cannot be done in a sort of manual fashion, what we have developed what we call as automated radio telescope imaging pipeline RTIP, which we have deployed in an automated processing, archiving and analysis environment. So starting from the ingestion of data to actually archiving and also to a large extent analysis can be done in an automated fashion. And for this we have partnered with software industry in India. ThoughtWorks, which is based in Pune, is part of it, and also we get a lot of support from our in-house team to keep this running. We actually have a dedicated 26 node cluster, each node having approximately 400 GB of RAM. That's the kind of setup we have, and this is now complemented by 4 petabyte of very fast storage with InfiniBand interconnect, and then at the same time we have supporting spinning disks of about 1 to 3 petabytes, currently 1 petabyte, but will go to 3 petabytes hopefully soon, and then additionally tapes. There is also tape archive, because all the data that we get from observations, every few months we get it from South Africa over tapes, because it's too much of data to actually download. It's not possible to do that. And all these details actually about the pipeline, if you are interested, they are mentioned at our website and also in this paper. This is just demonstrating here. I'm not going to go into the detail. It's all again there in the paper. Is that when we want to make continuum images or we want to make spectral line cubes, there are different parallelizing approaches that we have to take, because in case of spectral line processing, it can be tackled in an embarrassing parallel manner, and it's very easy to progress through it. It becomes more of a problem of managing the workflow and the products. But in case of continuum imaging, then it's much more memory intensive. So one needs to parallelize in a different manner. So all this needs to be taken into account. So to get this done, if I just briefly tell you that. We are observing total close to 800 / 1,000 pointings. These are coming over a period of, let us say, 3 years. This means that we need to be able to process all the data products for one pointing per day. So this is how we are closing this loop actually. This simple statement actually in a very simple manner states what is the data processing challenge that we have and how we can optimizing using different data processing and hardware in place. And for last 6 to 8 months, we are able to actually meet that requirement. So this is quite exciting. So this is a summary of whatever we have talked about. The footprint we have talked about here, this is how it looks like. It's all done, L-band already observed, and we are also able to tackle the data challenge that is involved with it. Right. So now let's move to early science and the data release part of it. So this is the first spectra that we took. This was in 2020. Actually, this first panel here is showing the UHF band, and these two panels. And so you can see that this goes on from 580 megahertz approximately to 1060 megahertz. That's the coverage of the UHF band. But in terms of redshift, it is corresponding to 0.4 to 1.4. So right, in terms of redshift coverage, it is huge. Actually, very precious for our survey. And when we come to L band, then it's again going from you can see approximately 900 megahertz, and it's going up to 1670 megahertz here. So and you can see that in L band there are some portions which are affected by RFI, but a lot of it is actually free. And this target PKS1830-211 is also known as UT lens. It's a very popular source, actually has been known since early 90s, and we selected this because it already had some two H1 absorbers known, so we thought it's a very good object for science verification. But when we observed this with actually Meerkat, because the Meerkat as an instrument is so sensitive, that we also made new detections of actually OH satellite lines. So these lines, so this is essentially the highest redshift detection of these lines, and this is what is shown here, that there are these 4 OH transitions which are supposed to have certain LTE ratio, but we find that the satellite lines are actually out of it, and if we take this particular 1720 megahertz line, it actually corresponds to the most luminous maser that we have. Has been detected till date. We can actually use the high frequency and low frequency maps of which are shown here of this lens, and actually try to predict what kind of absorption lines we expect to see as centimeter wavelengths with Meerkat and with ALMA at millimeter wavelengths, and we can actually do a pretty good job of reproducing these observed properties. But at the same time, in the H1 disk, we need to introduce an additional velocity dispersion. So it's a very nice demonstration of how we can actually start making connection between absorption lines and galaxies as well. This is another first that has come out of Meerkat survey very recently. This is the first unambiguous detection of the hydrogen radio recombination line. This is obtained actually by stacking about 40 to 50 lines covering entire L and UHF band. So this we are quite excited about this, because in addition to H1 and OH, which gives us probes for atomic and molecular gas, we are now also will be sensitive to at least put some constraints and detect some new radio recombination lines with the survey as well. This is a new detection coming out of survey at 1.3. Demonstrating the power of how things can be turn out to very different if we do a blind survey. This side is all showing the radio spectra, continuum image, spectral index here, and here we are seeing the new detection that has come out of it. If you look at the same object here, is quasar here. If you look at the optical spectrum of it, you can see that there is nothing which is seen in here. So there is a large gas reservoir in this case, which is missed in optical due to low covering factor, because in optical we are shooting one sight line, and we know that at radio we can have very large covering factor coming from radio lobes and cores. At very low redshift, that is redshift less than 0.1, we can actually detect H1 emission directly from galaxy. You can see that this is an example of a galaxy group, and here happens to be a quasar here, so we can also detect 21 centimeter absorption from it, and we can model the disk of this galaxy, kinematics of it, and we find that the gas that we are seeing in absorption actually is more like the gas which is extraplanar and not necessarily from the disk. Again, a very nice example of it. This is another example in connection with cosmic ultraviolet baryon survey, which is actually targeting fields which are centered at high redshift quasars for other experiments like observations of CGM at optical. Here again, like in this panel, we can see that H1 emission is detected. These are two dwarf galaxies. You cannot make out that they are interacting from the optical image here. And again, the absorber that is detected in ultraviolet, in this case, we can from this interpret that it is actually coming out from the gas that has been pushed out of the galaxy because of the interaction. So these are the important connections that we need to make between galaxy, the gas, where the origin of gas is, and what we see in absorption line, to be able to interpret. And in that sense, MALS turns out to be a very efficient survey that it can actually do all this science that is needed to interpret. But from the survey, we also detect several thousand galaxies in H1 emission. This is one example of showing DH1, that is the H1 size and the mass of these galaxies. You can see this is one of the very tightest correlation known in astrophysics, and what we are trying to do here is to understand actually that if this relation actually changes if we go from one type of environment to another. And since we are actually observing from through the galaxy, all these sight lines are actually also probing our interstellar medium. We can actually of our Milky Way, and we do detect H1 and OH. We detect actually H1 in 80% of the cases, and we also detect OH main lines in few percent of the cases. This is very easy to understand. That is actually physics of OH in diffuse ISM can be very easily understood from a very simple reaction network, and one can say that like the OH detection rate is supposed to be something like that. Since we have a very broadband frequency coverage, we can actually do polarization as well, and this is showing an example of an extended radio source, which is actually has sight lines passing through the outer H1 disk of a galaxy, and we can see that like in the Faraday space, different kinds of complexities are seen here in this case, and from this we can actually try to understand that what is the kind of magnetic field or electron density. Actually, it's the NEB parallel is how this is actually different across different sight lines. So this is another aspect of it. So this is my summary slide of whatever we have done till now. We are now moving towards the data release. This paper is submitted. We have got referred for. This is supposed to actually come out. Probably will make a data release in a couple of months' time. It consists of 500,000 sources, properties at 1 and 1.4 gigahertz. We have confirmed and obtained very accurate source count from here. This is showing that actually the survey is consistent with what we expect in terms of astrometry, flux density, and everything. So a very important milestone in that sense. In addition, when we compare this with NVSS, the brightest of the sources, that is, we detect actually close to several hundred variables and transients from the survey. And we also find that as we go towards lower flux density, this is Millijansky here, the x-axis is cropped here, but as we go towards lower frequent flux densities, we see that there is a flattening of spectral indices. This means that the radio source population itself here is changing. So the big idea here is that we can actually combine this with how the H1 properties of sources themselves are changing. So this is actually can be done at a very highly statistical significance level. And this is the summary of my slide. Thanks.
Thank you very much. Questions?
Can I go ahead? Yeah, so I just wanted to ask basic question here.
I cannot ask who is asking. Okay. Hi.
Okay, so the time scale of accretion of IGM or CGM, is it comparable to the stellar evolution time scale in the host galaxy?
No, they are happening at a very different time scale, and the time scale over which it actually gets converted into molecular gas in stars is also very different actually. So we will have to, if we want to compare all these different scale, we will have to combine it to what people are observing CGM and IGM at other wavelengths.
Okay, and I also noticed you mentioned about multi-layered data storage. So how did you arrive at that solution? That is, which layer should contain how much amount of data?
Yeah, so we can predict the size of raw data. We can predict the sizes of what the raw data product, that is quantum images and spectral cubes, will be. So when you are doing data, so you need fast storage only for data processing, not for archiving or long-term storage purposes. And since I described that we have 1.5 petabyte of raw data that is coming, so we would like to have it on the fast storage 1.5 petabyte, but why go for 4 petabyte of fast storage? Because when you have raw data, you end up making 2 or 3 copies of it because it goes through the cycles of calibration and everything, right? So that gives 4 petabytes, and that's how this number is worked out. We can talk about this in more detail if you're interested afterwards.
Okay, thank you.
Okay, second question.
I think I have missed, but can you please give some details about the UHF band, what area it is covering, and how much sensitivity is like?
Right. So Meerkat band. So, UHF band covers 580 to approximately 1060 megahertz, that's in frequency. And we are observing at L band for 1 hour, but we are observing at UHF band for 2 hours. That is because UHF band is slightly less sensitive, and in both the bands with this 1 hour and 2 hour respectively, we get a continuum sensitivity of approximately 10 to 15 microjansky in continuum, and in spectral line it will be half a millijansky per beam for a spectral resolution of 5 kilometers per second approximately.
And it will cover the same area as L band?
No, it will go lambda by d actually.
Lambda by d,
So 1.4 gigahertz is 1 degree, so at 580 megahertz it will be factor of 3 more.
Yeah.
So 3 degrees it will extend. That's why I said UHF band is where the sweet spot for spectral line searches and continuum imaging is, because sky also gets brighter, right?
Yeah.
Because of the
and what is the
non-thermal
procedure of distribution of data? What currently you have? Like, how will you?
Yeah, so this our survey website maths.iuca.in through when we will make the data release of these 500,000 sources, these you will be able to download all the catalog, you will be able to download all the cutouts for different sources. From that you will be able to make selections of different on the basis of different properties of the sources. So this is how it will be. You look at any survey, you look at SDSS, you look at Galax, you look at FIRST, NVSS. This is how it is distributed, and this is how it will be done for this also.
Okay, thank you.
One last question.
Hello, sir.
Hi.
So for 200 millijansky source centered at the phase center, for microjansky level noise, you need high dynamic range. What kind of imaging strategies, like advanced imaging strategies, will help to achieve this?
So, first thing is to have a very good instrument actually. So MeerKAT is a very nice stable instrument, and we don't really have to do anything special here to get a dynamic range of 10 to 5 or so in this case. The only places where we have to do anything non-standard is when there are strong sources which are off axis, right? Because then there are additional sources of errors come in, and that's why we'll have to make some directional dependent corrections in that case. But otherwise, over the entire field of view, you can get a very nice imaging property with MeerKAT.
Thanks.
Let's thank Neeraj once more. We move on to the next speaker.
Thanks.
Next we have Amitesh, who will tell us about odd radio surveys.
Hello. Just wait. This is okay. And where is the pointer? Is separate. Okay. Thank you. So this talk is about odd radio circles, or ORCs. And these are new sources which have been discovered in the sky a few years ago. And many scientists are sort of scratching their heads to understand what these sources could be. And these discoveries are made, no doubt, using the best telescope which we have presently, the square kilometer array and precursors of square kilometer array. So the discovery was actually made with the SCAP, which is part of that is in Australia, and the part of SK which Neeraj just described about the MeerKAT. Some of the follow-up observations were carried out with MeerKAT. So all these discoveries are coming with this telescope. Before I go and show those images, first see what changes these telescopes are bringing. Okay. So this is, let's say, one of the very old survey which was existing in the southern hemisphere, some survey, and this is the image from ESCAPE. Okay, so you look at the same. This is the same field. Look at the sensitivity improvements, not just in terms of the sensitivity in terms of flux density, but also in terms of the resolution, angular resolution, and that's very important because once you go and fill up lots of microjansky sources, your sky is completely filled, and you need to isolate these sources. And so this is really driving these discoveries, that we can actually see lots of details about these sources which were previously not even detected. So this is the discovery image of odd radio circle. What we see here, this blob, this greenish emission is the radio emission, and the background is the optical image. And there are many different objects in the background. We actually do not know, so this is, we have no three-dimensional information here. It's just, we are seeing everything in projection. But there happens to be a galaxy in the center for which the photometric redshift was known. That's about 0.5. So if you consider this source is actually associated with that galaxy, then it's about half megaparsec wide, okay? And that's a angular diameter is about 1 arcminute or so. And so this is something which has not been seen before if this is associated with a galaxy. So that's a big if. We will explore this. And that's why this made a big news everywhere. The media houses and all that picked it up and said, okay, what it all about. Now, just quickly running through this. So the ESCAP detected actually a number of sources. So particularly this one, and the first one, which is ORC 1, 2, 3, 4, 5. This is the image later on follow up with the Meerkat to get a very high resolution image. And this was actually detected serendipitously in GMRT archival data in one of the cluster field. Okay, so it was definitely, the image was existing, but nobody actually pointed it out. And then this is another image. Well, I was just looking at some of the LOFAR images, and I found again there is something very similar structure. So okay, these are the only ORCs which are presently known. Okay. Now, what we see already that there are two categories emerging, one with the which has a radio and optical source in the center. For example, number 1, 4, and 5, there is a radio source in the center, as well as there is an optical galaxy. But there are some sources which do not have a radio and optical counterpart at the center. So, for example, this double source and this another galaxy. Okay, certain things, the discovery paper by Ray Norris actually made a very detailed arguments about what it could be, what it could not be. These are all guesses based on our previous understanding. So there is no diffuse optical emission associated with this radio emission, and that rules out a few things very quickly. Is a galactic planetary nebula, because we do not know where they are presently. Although there is a galaxy in the center, but that could also be a chance superposition. And it cannot be a face-on galaxy or a ring type of galaxy just because there is no associated optical component. Another interesting thing is that these sources are at very high galactic latitude, so this doesn't go in favor of any galactic origin of these sources, particularly the supernova remnants, because you might have noticed that they actually look like a supernova remnants, and this point I will come back in a moment. They could also not be cluster halo, because they also look like a cluster halo. That's because these are not in the cluster environment. So these are all best guesses. This is nothing exactly to rule out, but it's just all kinds of best guesses what we know already. Radio galaxy is something which we, I think, be very careful in dealing with. Although the discovery paper ruled out that these are not radio galaxy, but I think later on our understanding is that we should actually keep it on hold. Some of these could actually turn out to be radio galaxies, particularly the remnant ones seen in a very different view than in the normal what we perceive about the radio galaxies. For example, this is just I'm putting some known cases of radio galaxies. Suppose this is seen edge on, so you are just seeing the lobes, and that could actually appear like a odd radio circle. And radio galaxies come in different morphologies. I mean, there's a whole zoo of radio galaxies. So I think we should definitely not rule out completely that these are not radio galaxies. Now, Meerkat actually made life a little easier about these sources, particularly the ORC1, which has been now studied in detail. Other sources have not been studied in detail so far. So this actually shows the polarization, the fractional polarization which is seen in the radio emission and that is at the edge you can see the fractional polarization is high, reaching about 20% or so. And this is the magnetic field vector. Again, you see that there is a well-defined, it's actually following the ring structure. And that is something we know already, that particularly the supernova remnants actually do show very similar structure. So definitely, this proves two things, that the emission is from the ultrarelativistic electrons, synchrotron emission, and this is very likely associated with the expanding shell or lobes created out of some explosion. Now, what is my take on this, although the number of sources are only few, that at the moment we need to view these as a heterogeneous morphological class of object, and I think we should not make a mistake that we start associating that, okay, ORCs are this kind of sources. No, it's just a morphology which we have seen, and they could be explained by a number of mechanisms. So with that in mind, I think there are lots of ideas in circulation. A couple of papers have been come out on this. So the very first thinking in the discovery paper by Norris was that in terms of energy required, and that's why the energies are going to be high to create a half megaparsec structure. And so the very first, everybody thinks of supermassive black holes merger, because these could actually power up lots of things, as we know. Then the idea is that if there are two merging galaxies, whether the shocks created by very violent interaction between two mergers could create that, and there are some arguments made. So these are very preliminary, arguments. There is nothing detailed have been put. And there is another idea that this could be a very intense starburst with hot winds blowing out, order of magnitude higher than what we normally see in nearby galaxy, and that could form the termination shock in the IGM, and that could actually look like a ORC. So this is another, idea. Now, I particularly looked at few things that what this could be, that are these supernova remnants, but not in our galaxy, but sitting just outside the galaxy, and I will come back to this point. And another idea is that whether these could also be the burst of TDs, tidal disruption events, near black holes in a post-merger environment of two galaxies. So these 2 points we will come. And the last is, of course, the radio galaxies, not to forget that in some spatial orientation at a very late stage of evolution, particularly those ones which do not have an optical source. Okay. So ORCs, if you look at, they definitely look very similar to the supernova remnants, and so this is particularly in the galactic SNR, and this is the SNR in LMC. This is the radio emission on H alpha, H alpha contours on the radio emission. So they actually look pretty much. There is a lot of similarity, and we always think that what it could be. Now the problem here is, if we understand them as a galactic population, we know that most of the supernova remnants, almost all are concentrated within plus minus 20 degree from the galactic plane, and these ORCs are detected at high galactic latitude, very high galactic latitude. And so if you just extrapolate how many supernova remnants you expect at very high galactic latitude, this just doesn't fit into that. So we don't expect these ORCs as a supernova remnant. So because this is the number, the observed densities of ORC is about 1.6 per 100 square degree, and that is way too high to explain as a extending population of galactic supernova remnants. So that's completely ruled out, that these are not the galactic plane population. So the thing is that, can ORCs reside in the Milky Way halo or just outside the halo? And that was the paper that I put in last year. And the idea here is that we know that the galaxies are not just the plane. There is a lot of halo population of a star, and this has been seen in external galaxy. You see there is a well-defined tidal tails produced. So, and some of these stars could go as supernova, particularly the type 1A supernova. So, I'm not talking about the core collapse ones. And this is the picture about the Milky Way halo also, that particularly the Sagittarius dwarf galaxy is supposed to have caused a lot of tidal streamers around the galaxy. So what are these stellar population which is existing? And the SDSS supernova survey has already detected a large number of intergalactic supernova. So we know independently that such supernova do exist. So this is a simulated view of our galaxy, that this is just the disk, and then there are lots of tidal streamers which are going around from as a the signature of the past events where the galaxy might have crossed some other dwarf galaxies or any other object which might have crossed our Milky Way. So I'm just putting this number. So how many? The question is how many intergalactic supernova we expect in our local group of galaxy, and that's actually a hand waving sort of argument just to get a order of magnitude number. So if you just take typical density of IgM and temperature, a supernova actually can expand a few hundred parsecs. So remember that in galactic plane, because the density is very high, the ISM density, the supernova do not expand much beyond like few parsec or 10 of parsec. But once the density is lower, the resistance is low against the expansion, and then they could grow actually to few hundred parsec. And then we can just put the same argument what we do in galactic plane, and then we can work out about this their radio surface brightness and sizes, and we can constrain distance. We can put a very rough constraint here that they could be as close as something like 300 kiloparsec or as far as something like 1.5 megaparsec. So this is based on what our understanding is about the supernova remnants in the galactic plane. And similarly, if you work on the radio power argument, then this could be at a distance of like 100 kiloparsec at the minimum and 3 megaparsec at the most. And as I said, that SDSS supernova survey has detected lots of intergalactic supernova just in extragalactic distances, and we just extrapolate that if a radio detectability of a supernova is not more than 10,000 years, then we expect about of the order of 54. Well, this is not an exact number. This is just to get an idea of whether we expect some supernova remnants to be visible or not. So we expect around 1.3 supernova every 1,000 square degrees. So that's the problem. The ORCs are at much higher rate. So they are detected at around 1.3 every 100 square degree if we just extrapolate that. And so supernovas are supposed to be more rare than the ORCs. So this is not completely explaining this thing. And in fact, this is just a paper which I put in SK issue, that what are the detection possibilities of these intergalactic supernova remnants with the full SKA. And that actually says that we can actually detect when the full SKA comes lots of these objects. Okay, let's first now go to what are the energy requirements. So if we have a blast wave propagating in low density IgM, we can actually work out just from the supernova arguments, because these are the equations which describe supernova are self-similar. We can sort of scale it up or down and just get an idea of what kind of energies we need. So if these are about 500 kiloparsec, which means that if we associate this radio emission with the optical galaxy, we require energies of the order of 10 to power 57 to 10 to power 50 erg in typical IgM density. So one can take a range of IgM density. You start with 10 to power minus 4 particle per centimeter cube. You can go to 10 to power minus 5 or whatever number you want, and just calculate the thing. So there is definitely a range, because we do not know what kind of density they are there. So we just take the typical IgM condition and get a rate and get a energy. Or we say that if these structures are synchrotron emission in low magnetic field, then they could survive not more than 100 million years at the most. And so in 100 million years, what is the energy rate which we need to continuously inject so that we still see the structure visible? And that's of the order of 10 to power 42 to 43 erg per second. So both the arguments, the total energy required in a short time like 100 million years just comes out to this number. So definitely this is much higher than what a supernova provides. So the question is there any other energetic mechanism like supernova which can work? So that's again just a out of the box idea that there is in fact the tidal disruption of stars, and that's something another paper which I put. So this could be the second possibility according to me. So what is the tidal disruption of a star? As we know that if a star comes very close to the black hole, part of that actually falls back, which we call the bound debris, and there is a lot of interest in the community, transient community, to detect these TDs but about half of the material is actually unbound. It just comes at a very high speed here, it is gains, and then it remains unbound. So it is just thrown away. And if you look at the basic how the tidal disruption works, is because the tidal radius and the Schwarzschild radius, as long as the tidal radius is larger than the Schwarzschild radius, this event is going to happen, means that the material will not be completely fallen back to the black hole, but part of that can become unbound. So definitely this is going to work better, the likelihood of tidal disruption is higher if the black hole mass is lower. So for example, at 10 to the power 8 solar mass black hole for a 1 solar mass star, there will not be any tidal disruption event, because this will be, because there is no tidal radius. The Schwarzschild radius is higher than the tidal radius, so nothing will come out. And so this actually tidal disruption works, as we know, at lower black hole masses. So that's a very interesting scenario. Now the tidal disruption events energies have been already worked out. So the ejecta could go at as high as few thousand kilometers per second. So let's not take this number as exact number, because they are estimated under certain assumptions. But this is the order of magnitude, that few thousand kilometers per second, and that's a very good actually. And the kinetic energies which these ejecta can carry, and then finally that will be deposited somewhere in the ISM, and a shock wave can be created. So that energy is of the order of few times 10 to the power 50 ergs. In fact, there is a simulation which shows that the energy will have a range. It is not exactly one energy, but different ejecta will have different range, and it will depend on how deeply the star can come closer to the black hole, how the orbits are, how elliptical these orbits are. So this is for 1 solar mass star. So the takeaway from this is that these energies are not as small as we might have thought. This actually is not exactly what supernova can do, but very close to what supernova are doing, okay? Just within 1 order of magnitude of the variation. Now the problem is that we know in the Milky Way the TD rates are small. That's a very, very rare event which we see. So thing is that if we want to deposit a very high energy and create shocks, we need a very high rate of TDs in a galaxy. And that is actually there. This has already been discussed, and that comes from the fact that most of the TDs which have been seen, they are seen in post-starburst galaxy. So the galaxies where the starburst is not ongoing, but it had happened a giga-year or few giga-years ago. And that was anyway very surprising, that why TDs are preferentially found in post-starburst galaxies and not in the ongoing starburst galaxy. And so there are a couple of explanations, and the one which actually says that how to increase the TD rate in galaxy is that if there are two galaxies merging, there could be the two black holes which are coming together. So just look at that, how 5 minutes, right? 4 minutes. So how TDs actually work, that there is a central black hole and the star comes and circles around, it just passes, and that's why the rate is very small. But imagine if the black hole, when the two galaxies are merging and black hole is actually ramming through the disk. So suddenly the probability of some star getting within the tidal radius of black hole increases dramatically, and that has been worked out that by this paper by Sen, that this is about a million TDs we can see in few tens of million years. So that's a very large energy deposition. In fact, this is just a picture that shows that there are two black holes might be coming very close to each other. So such events are there, and that increases the TD rate to a very, very high rate. And there is another supporting mechanism when such things are happening. This paper by Madigan actually showed by simulations that the orbits of a star in such a merging system of galaxies become highly eccentric, and so the more and more stars are deeply penetrating, and that can further enhance the TD rate. So these two mechanisms actually say that the TD rate can go very high, like 10 to the power 5 to 10 to the power 6 per million year, and that's the energy rate is going to be very high. So what is the mechanism which could actually act in some galaxies in these special conditions? That if a large number of TDs are taking place in a short period in a galaxy, That creates conditions conducive to shock waves propagating in galaxy halo and to larger distance. The distance here is proportional to the what energy finally is being deposited from the TDs in the center. So this is again simulation which were done in the galactic context in the so these each one is actually a TD deposition, and the shock moving out. So just imagine that this is not a starburst shock, but this is actually created by a burst of TDs in the center, and that can generate a shock, a very strong shock condition, and the energies can actually match with the energies required for these ORCs to produce. So just to put the summary here, a number of possibilities have been presented, as I said, and I have not gone into detail of each and every one. But the real challenge right now is that to show some conclusive evidence that whatever mechanisms we have been saying in different papers, that they are effective in galaxies. So they can work just as a calorimetric model, that yes, energy can be produced by these mechanisms, and whether they actually do, whether that happen, and how frequently we can see, how often we can see, that's all has to be shown. So that's the real challenge in getting that. Now, ORCs need to be considered as a morphological class of objects, and that's again I emphasize that we should not just make up our mind that ORCs are these objects. No. Some of these actually could be radio galaxies, some of these could be the halo population or intragroup population of supernova remnants being detected now, and some of these could really be the megaparsec size blast wave around distant galaxies. So I think the key is that right now we are saying only with 6 ORCs, so that is too much, I guess. Already, number of ideas are more than the number of ORCs, and so I think we should wait till these deep radio surveys actually produce more and more ORCs, and then we, see what these objects are. Okay, thank you.
Thanks a lot. Thank you. Questions?
Hi, Amitesh. So from the morphological structure, here I am.
Yeah.
Morphological structure, it also appears some clumpiness.
That's right.
So if you have, probably you need a better angular resolution, but the distribution of the clumps, does it also provide you another parameter along with the, energetics to say about whether the TDs can also be responsible for such, size distributions?
That's right. So the TD goes in, so TD scenario is in favor of such things, because this is number of, so one star is when disrupted, it's not just single ejecta, it has multiple ejectas with different energies. So it can create their own, think about own circles of emission and their cross matching, whether the density enhancement can come.
So that way the time scales of these things and the spatial distribution of the sizes, because the size of the clumps also says a lot about the mechanism which generates the clumps to be in the first place.
So current understanding is that this is multiple events, not just TD. I'm saying whatever it is, not just TD, multiple events and then crossing in the intergalactic medium that could produce these rings.
There are instabilities also which produces the clumps.
Exactly. So multiple rings of emission, multiple episodes of emission is the preferred way to explain this.
I was a bit confused when you said that the observed density of ORCs is much higher than what is expected for high galactic latitude supernova remnants. So how have you estimated the estimated sky density? You have only 6 objects that have been detected.
Right. So this is suffering from a small number statistics. So I think it's about 300 square degree in a sky, and the sources are there. So that is the number which is coming from.
Okay. So they've not been found outside of this 300 square.
That's because the way survey has been designed. So ESCAP is looking at only, so this is part of the what we call EMU survey, which was sort of a verification survey. So these are detected out of that 200.
Out of the pilot.
That's right, 270 square degree, I think, if I remember, something like that. So this is suffering from a small number of statistics. That's right.
Okay.
Yeah.
Firoza. Yeah. I noticed that your morphology of the ORCs does not appear to be too similar to what you would expect from a tidal disruption event. A tidal disruption event necessarily will have a bow shock followed by a long stream of gases as if are tidally torn out from the star. Whereas you seem to have almost spherical, at least, almost spherical, near spherical symmetry in your ORCs. So I think you're maybe a little too hasty about dismissing them as not being supernova remnants. It's the only quantitative way in which you can say if they are supernova remnants or not would be to have an idea of the distance at which they are at and therefore their size, which in turn would tell you whether these are actually nebular matter expanding into the ISM at a certain rate and how old they are. If you have a handle on the age, then you would know whether they are remnants or not.
Yeah, so good, but just again I emphasize that not all ORCs can be explained as supernova remnants because these objects, so if these are actually megaparsec size halo around galaxy, because there is a galaxy in 3 cases sitting at the center of a ORC, so we can't ignore, it can't be a chance. So I'm talking about non-supernova remnants. So these are associated with galaxy at high redshift. So how do you explain half megaparsec size? So this is for that, those sources, those category of sources.
Yeah, Amitesh. Yeah.
Have you considered gravitational lensing? Because in some cases it looked exactly like Einstein ring.
Yeah, but this is, I just referred to the discovery paper, it actually rules out that this could not be Einstein rings and all that, just because of the kind of size, just the size I think is not in favor of it being Einstein ring.
Okay, last question here.
Yeah, Amitesh, I'm just curious, I mean, have people looked into the spectral index of these objects?
Yeah, so one case is there, I showed ORC1, so that's how the magnetic field and the polarization has worked out.
And that does not give us clue about like what kind of...
so these are steep spectrum, not these I should say, the ORC1 is a steep spectrum around minus 1.6 at the edge. So.
Okay.
Okay, one more last question. You have the one? No. I thought you don't have it. There.
Can I ask? Yeah, so in the polarimetry image, you had proved that the ORCs are actually expanding shells. Do you see that there are different parts of the ORC expanding at different rate, or they are all uniformly expanding?
No, we do not have velocity information here. So this expanding shell is just coming from what you expect the polarization structure or magnetic field structure in an expanding shell. That just comes from there. So we do not have velocity information here.
Okay, thanks.
Short question on this.
Yes, sir. I think now that we know some radio galaxy hosts are normal spirals, the probability of ruling out a host for this remnant is very difficult.
Yeah.
So this could be like spiral host which has created this lobe and remnants.
Yeah, I think I showed one case.
So
and
unconsciously or consciously, I don't know. That's why.
Yeah, this should not be ruled out definitely. Yeah.
Okay, we should thank Amitesh Omar for this talk. Thank you very much. Next speaker is Saurabh Singh, who will tell us about observing cosmic dawn to 21 centimeter signal.
Okay. A very good morning to all of you, and thanks organizers for giving me this opportunity. So I'll start off with some of the experiments that we are working on towards detection of 21 centimeter signal from cosmic dawn and epoch of reionization. But before we deep dive into the details, this work is a collection of vast efforts from a lot of people, and I would really take this time to acknowledge them, along with very active support from different field stations, including IAO Hanle and Gauri Field Station, and a lot of facilities at RRI. So with that, let's get going. And really, it's a cosmology talk, so it has to start with a timeline. So what we are really looking at are redshifts of around 50 to redshifts of around 6 or 5. And this is the period when we expect the first stars and galaxies to form. So just before that, we have a lot of information coming from Planck WMAP about CMB, for example, and we have a pretty good understanding of this slice here. And of course, with a lot of local surveys, we have a lot of information about this. Of course, we still don't know a lot of things about dark energy, but we are trying to map this part as extensively as possible. But this intervening part is something that's really ill-constrained at this moment. And that's where we expect to gain a lot of understanding by 21 centimeter signal, just because hydrogen tends to be the most abundant element. So we start from here when the very first stars form. And when these structures form, they do two different things. One is they release ionizing photons. And with that, they start at some point to ionize the intergalactic medium. Of course, it's a very slow, extended process. So it's expected to be ending around, say, 900 million years or so after Big Bang. At the same time, it's also changing the thermal state of IGM because the first sources of radiation also emit X-rays, and they heat up the gas. So in some way, by using this 21 centimeter radiation, we are trying to track the ionization and thermal history. So why 21 centimeter signal? One of the distinct advantages is that it gives us a very fine time information. We know the rest-frame frequency, and we know at what redshift we are looking at. So we can exactly predict at what frequency we are going to observe it. And in some way, it's like a Swiss cheese analogy. It gives a lot of spatial as well as temporal information of the evolution of IGM state. And this is what we really measure, not going into the details of this equation, but there are two quantities of emphasis. One is the neutral fraction. So of course, the strength of our line would depend upon how much gas, the neutral gas, is there in IGM. It also depends on the spin temperature of the gas in contrast with the background radiation. And in the early phases, around cosmic dawn, we are really dominated by this term. So we are tracking how the gas is getting heated and coupled. And in the later stages of EOR, the reionization aspect, we are dominated by the neutral fraction because suddenly we see that the hydrogen is getting depleted at a very rapid rate. So this is what we aim to measure. And what is it observationally that we are looking for? Well, we are trying to measure a field, a brightness temperature field of 21 centimeter. So we can do lots of statistics with it. The most popular ones in this field are the power spectrum and the monopole or the mean signal. So from here, the power spectrum intends to measure the fluctuations. So at a given redshift, what is the morphology of the brightness temperature or therefore the gas? And for the monopole, it's a more simpler measurement. We are averaging the entire spatial axis into a single number and asking what's the mean brightness and how it changes with redshift and therefore as frequency. So switching to an observationalist hat, what kind of instruments do we need for this? For monopole measurement, we only need one single antenna, right? Because we are measuring one number per redshift. And we don't really have a lot of constraints on spatial resolution because we are averaging the sky. So as long as the antenna is well calibrated, something I'd really come in the later part of my slides to, we should be able to get this signal. Measuring the power spectrum, which captures the fluctuations, is slightly more tricky just because we need spatial information as well. And therefore, we need interferometric observations with certain baseline distributions to capture those scales. And again, in my talk, I'll kind of contrast between these two kinds of experiments that I'm associated with and what kind of results we have got from them. And why are we so interested in this? And the reason is that this specific signal captures a lot of astrophysical information which is yet completely unconstrained. So this plot basically varies a lot of astrophysical parameters from ionization efficiency to the minimum mass required to form halos, X-ray properties. And the two panels shows how the power spectrum and the middle panel shows how the global 21 centimeters signal changes by changing those properties. So in some way, the idea is to be able to detect this signal and reconstruct a lot of astrophysics from that signal. And one point to note is these are two very complementary measurements, and therefore, we should be aiming to be detecting both to get the complete information of what the field is. And this is just a summary of what kind of different signatures we observe. And this is where it gets slightly different from more cosmology signatures, which are very deterministic from, if you assume lambda Cerium, for example. Well, in this case, because there is a lot of intermixing of cosmology and astrophysics, that too very poorly constrained, we can have a range of signatures of the 21 centimeter signal. And that's why this becomes more and more interesting. The left panel is more standard models by changing the X-ray and Lyman alpha properties of the stars. And the right side, as you can notice from the amplitude, are very non-standard and exotic models. They have their own importance, which I'll come to later in my talk. So, focusing right now on the monopole or the global 21 centimeter signals, there are lots of experiments going around. Again, all of them having some similarities. For example, all of them are single antenna systems located in very remote corners of the world. And really, this field is flourishing. There are lots of other experiments that are coming at horizon. And we are expected to have a lot of interesting results in very near future. So the one that I'd be talking about today is CERES-3, which is in-house designed and developed at RRI, along with touching upon some other power spectrum measurements and our more space-based proposals. So what is the basic challenge of these experiments? I really like the optimism here. So the foregrounds are really bright, and this is something that we well know at these frequencies. And they can be 10 raised to 4 to 10 raised to 5 times higher than the kind of signal. So here is just one template of what the foreground should be as measured by a global 21 centimeter experiment. And these different colored lines are what the 21 centimeter signal itself looks like. You can already see the contrast. Though I should mention this is not really the fundamental challenge, because the spectral nature of the two components are very different. And we can really exploit that to extract the signal of our interest. The problem, as usual, arises because we have a telescope in between. And that's what basically modifies the intrinsic spectral properties of these signals. So there are different ways in which instrument can actually imprint its signatures, starting with, well, RFI. In radio astronomy, I think we all know well enough now. And then, of course, antenna is on some media, so it does interact not just with the sky signals, but also with the signals emitted from its media. It can have a field of view which is frequency dependent, and that can really lead to mode mixing, which is a lot of spatial brightness structures that you see in the foregrounds can actually come into spectral modes. Then we can have standing waves because we have impedance mismatches in our system. We can have self-generated RFI. We can have issues related to analysis. So there are different ways in which things can go wrong. And really, all it needs is one thing to go wrong in order to compromise the detection prospects. Because if you look at the dynamic range, we are talking from 10,000 Kelvin to something which is 10 millikelvin. So at RRI, we are trying to tackle all of these challenges via two different experiments, having very same science goal, which is detecting this 21 centimeter signal from cosmic dawn. CERES is a ground-based experiment, and Pratush is a space-based proposal to ISRO, and I'll briefly touch upon both of them. The design philosophy of the telescopes that we design is roughly similar, which is we know that the foregrounds are spectrally smooth because, first of all, they are broadband emissions, and we are averaging over a large part of the sky. So our instrument response needs to preserve that, and that basically enables us to filter out the foregrounds. So the blue line, for example, is the foreground, red being one of the 21 centimeter predictions. If we just fit out the smooth spectral mode from this data, the data that has only the foreground term goes down to the noise, sub-millikelvin. But if we apply the same filter on the signal, we are left with a lot of it. So as long as we are able to preserve this spectral difference between the two, we should be able to detect the signal, and that has been the driver for the kind of designs that we have. So these, in some way, these experiments are actually very similar and very simple by construction. All it needs is one antenna, an analog and digital receiver. But as you can see, there is a fair bit of sophistication that comes with the calibration. So we do want to remove any kinds of band pass effects or contamination that comes from our own instrument. So just below the antenna, we have these analog receiver, and this forms a single unit that you may have seen here, right here. Some distance away, we have rest of the analog electronics, which is basically the filtering and amplification, followed by a digital spectrometer that does the Fourier transform and gives us the sky spectrum. But at every stage, we have taken sufficient care so that any kind of contribution coming from the experiment should not have a spectral mode that lies in the 21 centimeter signal. Or in other words, it should not introduce any of the signatures that we have seen in the 21 centimeter signal, because again, a small miscalibration can really lead to either no detection or a false detection. Sorry. So yeah, so there are different things we have done, for example, extreme miniaturization, having optical isolations, having some phase switching for cancellation of systematics, and so on and so forth. I probably don't have time to get into the details of this. But now, given this design, Ceres itself, it's not the final design that just came out of nowhere. It has its own series of evolution. So the first version of Ceres was deployed in 2010, and as you can see, it was a very different system altogether. It was a dipole antenna to start off with, observing in Gauri Binnur field station. But with time, instrument has changed, sites have changed, observing media has changed, and so on. And with each deployment, we gain more experience of how to make our calibration better, and therefore things just keep on changing. And by no means this is the final design. We'll probably have more and more pictures, maybe in further meetings of ASI. So, as I said, it's a simple system, antenna, analog receiver, and digital receiver. One of the key differences between Ceres and other experiments worldwide is the observing media. It really floats on water, which is very different from other telescopes. And the reason is, of course, we started off with land. But the problem was that the antenna was very sensitive to the profile of the ground itself. So if you have stratification, for example, it can lead to a lot of systematics that are very hard to model unless you know those ground properties perfectly. So we started looking at geological surveys and whatnot, and none of those have the accuracy that we need to model them. So how it changes? So this is just one of the schematic done by our research assistant, Kavita. So this is one of the crucial antenna properties that many of us might be familiar with. It's S11, or rather, in some way, impedance of the antenna. And when it floats on water, our impedance changes like this, the blue line. If it's on a uniform ground, for example, it's like this orange. But the moment it has stratifications, it becomes like this. And any of these changes, if even there is a miscalibration in 1 part in 10⁶, can lead to very false detections. And that's why it's very important for us to control the media on which the experiment observe. And the easiest system to observe is the one which is more uniform and homogeneous, because it's just easier to model that way. Of course, the next best, this is next best actually. The best thing is to have antenna in vacuum, which is one of the most pristine sites for us to model its response. Other problems that relates to the ground-based systems are, of course, RFI. So this was one of the measurements done by Radio Astronomy Explorer. And these are all decibel units. And even the lowest of the units here, for example, is much higher than the galactic foreground, which itself is way higher than the signal we are looking for. So RFI remains to be one of the biggest problems. Ionosphere, of course, has its own set of problems, and it probably requires a talk of its own. So there are sufficient reasons why we would also want to do this from space. And that's where Pratyush comes in. So this is a second experiment, very similar to Ceres in its science goals, but very different set of considerations have gone in here. So Pratyush is a proposal to fly a radio telescope eventually in the lunar orbit, noting that there are these fundamental constraints for the ground-based experiments. And again, the construction is similar. It has its analog and digital systems along with spacecraft electronics right here. And we are happy to share that our lab model is already in place and it's undergoing rigorous testing. This is what the lab model looks like right now with analog and digital systems. Of course, it's not all a bed of roses. Space-based experiments have their own set of problems. So for example, unlike Ceres, where you could separate out things to reduce electromagnetic interference, that luxury no longer exists. Everything has to be compactified into a single system. So that really increases a lot of constraints on the shielding. Of course, we are operating in a very limited parameter space, very limited power, very limited mass allowance, and so on. And one of the most important part is the antenna properties. Antenna is not just what it sees, but also all the metal which is around the antenna, right? So antenna design cannot be done as a standalone thing. It has to be co-designed with everything around, including satellite bus, solar panels, communication antenna, and everything. So it keeps on evolving as the nature of the experiment changes. So the current status is that we were funded by ISRO for our pre-project studies phase. And as I said, lab model is already in place. Our first proposal is as phase 1 to fly in low Earth orbit. And this will be basically giving us some bands where we can actually demonstrate the sensitivity that we can reach with this payload. But eventually phase 2, we will aim to fly in the lunar orbit and observe from the far side of the moon, which is really one of the quietest sites in the solar system to conduct such observations. So with that, I'll switch gears and now talk about some of the findings that we had with our ground-based systems. So CERES started observing in 100 to 200 megahertz, corresponding to redshifts of 10 to 6. And this was done in around 2017 with a monopole antenna that you can see here. So we had some 60 hours of data, which finally led us to sensitivities where we can look at different kinds of signals, whether they are consistent or inconsistent. So this probably I showed this figure before, which is all different kinds of global 21 centimeter signals that are possible. And of course, this parameter was completely unconstrained before this. The colored signals are the ones that we ended up ruling out from CERES-2 observations. And they do share a common astrophysical scenario, which is you can see they are all deeply absorption based, which essentially means that the IGM is very cold, and therefore contrast between the spin temperature and the background is very high. So in some way, we are placing constraints on how well can X-rays heat the gas at those redshift. You would also note that these very quickly go to 0, which basically is decided by how quickly the reionization is proceeding or how quickly the XH1 is going to 0. So we basically ruled out the scenarios where the IGM was very poorly heated and the reionization was very rapid. Lately, this work has been also extended by one of our collaborators, where not just the standard models, but we have also looked at very non-standard models that have excess radio background. And we ended up ruling out a very similar class of models. So the blue line, the blue curves here are the priors, which are all these unconstrained parameter spaces, including the excess radio background. And just using CERES-2 data, we could constrain all the way that's shown here. And we could put some constraints on FX, which is in some way quantifying the X-ray heating efficiency and the luminosity in radio. The great part is that the kind of constraints that we are deriving here is also very consistent with the constraints coming from other experiments which are doing power spectrum. That's something I'll again come back to in some time. Of course, we shifted gears in 2020 when EDGE's result came, and many of us are familiar here about it. They claimed a detection of this signal from the cosmic dawn, which was very anomalous in many, many ways. And none of the theories in lambda cerium could actually explain it. So there was a lot of work going on in order to evoke a lot of non-standard physics that included, for example, excess radio or even baryon dark matter interactions and so on and so forth. But really, one of the ways to investigate this is to have a completely separate measurement. Of course, there were also claims, including from our group, about how this was not a unique solution, and there could be different models that could be fit with the same data. So we deployed a CERES-3, which was re-optimized to operate between 40 to 110 megahertz. This, I don't have, the time to go into the details, but this is the final spectrum. We deployed this in North Karnataka at near Shimoga, and got around 15 hours of data, which is all average to show here after corrections for all the instrumental contaminations. What's our best understanding of the galactic and extragalactic background? And this is the kind of noise that we reached. In order to model it, we used some model for our foregrounds and residual systematics, along with the edges profile with a scale factor. And basically saying that if the scale factor was consistent with 1, we would have claimed a detection. But what turned out is that it was actually 0, which basically said that our model was consistent with the noise without any kind of edges signal. The scale factor was indeed 0. And basically, we ruled out at 95% confidence presence of any such flat profiles. So we are now back to lambda cerium and still hunting for that true 21 centimeter signal. Again, we have extended this work very recently to also look for other kind of physically motivated astrophysical scenarios from CERES-3 data. And this time, because we had better sensitivity, we could actually constrain a lot of astrophysical models that dealt with star formation efficiency and also luminosities in the X-ray and in radio. So when combining all of them, again, we have the same parameter space here, and by using CERES 2 and CERES 3 data, we could go down to a very narrow range of parameter space. Of course, still wide open relatively, and we are still looking for improving it and eventually detecting the true signal. Okay, so this is the final ruled out signals that we have from CERES. And of course, those gray signals, and of course, this is not an exhaustive list, so the true signal might even lie outside this whole parameter space, we never know. But that's the hunt that we are on to. Before I go to next session, just a quick survey of the power spectrum, because as I said, it's the same field we are probing, whether we measure the mean or whether we measure the fluctuations, which is the power spectrum. So I'm also working with Hera collaboration, for example, that aims to detect this power spectrum. It's an array of 350 meters dish. It's still in the commissioning stage, but it's also doing observations. And just very recently, we released our second limits. Of course, it's still a non-detection, but it's one of the deepest limits that we have obtained till date across all the different experiments. So this is the power spectrum as a function of different spatial modes on the sky. And what we see are we are largely consistent with the noise, which basically had around 94 nights of data. And based on this, we could also do astrophysical constraints because we were already at the regime where we can rule out a lot of different models. And this is where things get interesting because we have two very different sets of measurements, so CERES and Hera, for example, but at the end of it, the astrophysical constraints are very similar. So for example, on the left, we have the radiation temperature constraints, the axis radio, as a function of redshift. Of course, these are not measurements done at the same redshift, so there is a fair bit of model that has gone into it. Also, the spin temperature to the radio ratio, we are able to constrain both with CERES and with Hera. And of course, this is a general framework where we could also include other experiments. So this is a nice time when different experiments are also converging and putting up stronger constraints by combining the data sets. Okay, so where do we go from here? Since the last deployment, we have made several changes in CERES. Again, as I said, with every deployment, we get some sense of how to improve the calibration. So those changes have led to a great improvement in our sensitivity and also reduction in the spectral complexity, which is what we need so that the signal loss is minimized. So we have done all of that in the lab, and we have demonstrated that the upgraded receiver indeed performs better. We are also trying to quantify different kinds of systematic errors. Of course, if it's floating on water, it's not a very stable system to start off with. And any kind of lateral or tilts movements can have effect on the beam response, for example. And as I said before, if the beam is chromatic or if it's frequency dependent, it can lead to a lot of spectral modes. So we are trying to quantify all those errors and therefore translate them into, for example, how do we best deploy so that those errors are reduced. So for example, here Yash has worked upon a lot of these systematic errors. So what you can see, for example, if you have a huge tilt just from the foregrounds, which are intrinsically spectrally smooth, you start to see features at hundreds of millikelvin simply because your beam has become chromatic. So things like that we are trying to address and basically narrow it down to a range of parameters where we still are away from that chromaticity effects. Another front we are really struggling is the radio frequency interference. So the sites which were good before 5 years are no longer good, at least for the cosmology experiments. And therefore, we have also led campaigns at different sites to see if we have better options. So this was one of the snapshots, thanks to I.O. Hanle. I see many people from there here in the audience, so thanks a lot. We went around in those areas and did some characterizations of how quiet those sites are, and they turned out to be excellent sites, actually. So we are still trying to build upon our database to finalize which site we would finally do the science deployment. But in the meantime, we have already done test deployments in Karnataka at a couple of sites, and based on those, we have validated our receiver, the whole CERES system, actually, for the next phase of science deployments. And this is one of the snapshots of the site that we have found. So this is, for example, what is in Gauri Bidnoor here. And this is the southeastern Ladakh. So you can see in the 0 to 100 megahertz, for example, except for the OPCOM satellites, we really don't have anything, including FM lines. So this is, if you look at the occupancy, this is globally competitive with best of the sites, for example, Western Australia, and therefore it's really important to be preserving these sites for astronomy. So that's where we are, and I think I'm already over the time, so I'll leave you with the summary. Thanks.
Thanks a lot, Saurabh. Questions now?
Saurabh, thank you for the talk. Just wondering, do you plan your observations mostly in the night? I think, do you also look for moonless, Jupiterless nights, and how do you?
Yeah, so one thing that really helps us is our field of view being very broad, so we are talking 60 to 80 degrees beam. So a lot of effects that come from Moon and Jupiter are highly diluted, basically. So yeah, we do observe only in the night, but the only thing that we worry about at night is ionospheric activity. So we down select the nights that have TEC less than 15. But other than that, other sources in the night sky hopefully today are fine. Yeah.
Hi, Saurabh.
Yeah.
So if I understood correctly that the ASI's result doesn't stand, so can you elaborate a bit more, like how exactly was that conclusion made?
Yeah, so basically, again, this was a great test because we are at a very different site than edges. And so the whole idea of that deployment was to look for that flat profile, and not just that flat profile, but also probe the entire parameter space because they had this huge range of amplitudes and flattening. So we tried very hard to look for all of those signatures in our data and found none. Of course, we also did not find the true signal because our sensitivity did not allow for it, but we had enough sensitivity to probe the entire edges parameter space. So we are essentially ruling out the parameter space which was allowed by the edges collaboration.
Hi. So has edges come back with explanation of what that signal could be?
No, I mean, other people have. But so, I mean, from a plausible systematic point of view, people have worried about things like beam chromaticity, which is really one of the bottlenecks simply because you assume some kind of a global sky model, which we know are very inaccurate. So people have worried about that. People have also worried about ground plane effects because there are some discontinuities or just that there is a huge ground plane there. So some kind of ground coupling. But yeah, the real reason is not known yet.
Any other question? Okay, let's thank all the speakers in this session. Thanks a lot.
Thank you.